Hello everyone. So in this session, we will be discussing about the increase in parallelism. So in the previous session, we have discussed how parallel computers are modeled, and we have discussed the Prince classification, namely the four models: SISD, SIMD, MISD, MAMD. As a continuation of that, we will just now discuss about how to increase the parallelism. Why we are moving for parallel architecture? So actually, the parallel computer architecture adds new dimension to the development of the system by increasing the number of processes. Okay, so by involving large number of processes, it is possible for us to improve the overall performance when compared to the single processor computing. For that, in order to enjoy the benefit of multiple processes, the application, whatever we are going to run on the parallel machine, should be able to support parallelism. So that is an important key point that always has to be satisfied. Unless otherwise the application has the property of parallelism, we will not be able to make use of parallel computers to increase the performance. So now, how to achieve parallel processing? So it is one of the technique which makes us to perform simultaneous data processing tasks. And why we do simultaneously? Because we have to increase the computational speed. And to do this, we actually need multiple infrastructure, namely in terms of functional units, or in terms of processors, or in terms of computer itself. So it can achieve faster execution time by distributing the entire job among the multiple computers. It is possible to reduce the total time taken for execution. Okay. Here, the instruction can be processed by the ALU component of the CPU. And in that case, if the application is going to involve too much of arithmetic logic operations, and if we have multiple functional units, then at the level of the functional unit itself, we will be able to improve the performance. And the overall objective of doing this parallel processing is to increase the throughput. What is meant by throughput? It is nothing but the total amount of work done in a given unit of time. So this is a common definition for throughput. Now, with respect to parallelism, how you will define throughput? It is the total number of instructions executed in a given unit of time. Either could be by single CPU or by multiple CPU. So here, and again, the CPU which is going to be involved in multiple can be of same type or it can be of different type. If they are going to be of same type, it is going to be referred as homogeneous computers. And if it is going to support multiple categories, then it is going to come under the category heterogeneous. So here, there is an example how we can achieve parallelism. So that's what they have mentioned here. So to the memory, we will be through the memory we will be receiving the instructions and the data, and we will be having the processor registers to store all these data. And in terms of functional units, we keep mentioning multiple functional units. Here, the total functional units which are supposed to be there inside the CPU is an adder subtractor, which is required to perform addition subtraction operation, and multiplier that can perform this multiplication, and it can be exclusively designed for dealing with integer units, integer numbers, and there could be a logical unit which will be expected to perform all the logical operations, namely and or not, like that. And we have the shifter unit which will be performing the shift operations, and the shift can happen in two directions, either shift right or shift left. And usually multiplication and division can also be realized by shifting the operands towards left or towards right if one of the operand involved in this multiplication division process is going to be in powers of 2. And then we have the concept of incrementer, which will be always incrementing the value by 1. And these are the units which are going to involve integer operands. And if in case if it is going to have floating point operands, then we need a separate dedicated unit to perform floating point addition subtraction, and similarly for multiplication and division. So these are the multiple functional units which are expected in arithmetic logic unit along with the processor registers. Now, to implement parallelism, we can have these units multiple in nature, so that parallelly it can perform concurrent operation. So the floating point operations can be separated into three circuits as we have mentioned, one to perform addition subtraction, then for shifting, and then for incrementing. All the units, whatever we have discussed so far, are independent of each other, and they can be operated individually. So as far as the parallel computers are concerned, it can be classified into multi-core computers or multi-processor computers. What is the difference between multi-core and multi-processor? So first we will discuss about multi-processor. It is nothing but multiple processor, that means multiple CPU. So these CPUs are going to be laid on different ICs. So we are going to have multiple processor, and these processors going to be connected with each other by a common memory, or they can have a distributed memory with some assigned local memory. And if it is about multi-core, it is nothing but multiple processors lying on the same die. If the same chip is going to have multiple processor, it is going to call as multi-core. And if these processors are going to be deployed on different chips, then it is going to be called as multiple processor. Okay, so parallel processing or parallel computing can be achieved either by means of multi-core or by means of multiprocessor. And nowadays, we have multi-core architectures available in abundant, and this multi-core also supports parallelism. And again, this parallelism can be achieved at different levels. Okay, so it can be achieved at the bit level, or it can be achieved at the instruction level. And whatever could be the parallelism, the most important challenges or the obstacles that is going to limit the performance of the parallel computing is the communication and the synchronization task. So whenever we go for parallel processing, how we are able to communicate the information across different processors. That is, we have to distribute the load across multiple processors. How this communication is going to happen between them, and how they are going to do the operations concurrently in a synchronized manner. So this communication and synchronization are going to be the two major tasks that are going to be planned, it needs to be planned properly to obtain optimal parallel program performance. And now we will discuss about the different types of parallelism. As I already told, the parallelism can be classified as bit level parallelism, instruction level parallelism, task level parallelism, and data level parallelism. So coming to the bit level parallelism, here it is a kind of a form, it is a form of a parallel computing where it has increased processor size, and it actually reduces the number of instructions that the system must execute in order to perform large sized data. So actually we have the multiple data provided, and they will be able to execute multiple operations on these multiple data in a given span of time. So maybe, for example, they have discussed a scenario where we are going to make use of an 8-bit processor, and that is going to be dedicated to compute the sum of two 16-bit integers. So how it can be done? It will be able to handle only 8-bit at a time. So the given data, 16-bit data, is going to be split into two 8 bits, one lower order bit and another higher order bit. And if we have two units available as an infrastructure, we can feed these subunits of the data in parallel to these units and get the work done. So a 16-bit processor can perform the operation with just one instruction, and if it is going to be an 8-bit processor, then it has to do the same thing in a twofold manner. So if we are going to discuss about parallelism at the bit level, then it comes under the category bit level parallelism. Then comes instruction level parallelism. Here, at any point of time, the processor can provide only one address, and hence only one instruction can be fetched at a given point of time. And these instructions can be reordered and grouped together so that they can be concurrently executed without affecting the result of the overall program. So what we are trying to do, we are just going to look into the dependency of the instructions. If the instructions are independent with each other, we are trying to submit all the instructions, and they can be executed multiple at the same time. If there is a dependency across instructions, then what we are trying to do, we are just trying to reorder the instructions in such a way that there is no dependency. And once if we are able to achieve that reordering, then these instructions can be executed concurrently by the multiple processor. Of course, to implement this instruction level parallelism, we need the compiler support, because when we write the program, there could be always dependency. If dependency is there in our program, then the instructions have to be reordered. So the compiler has to be fine-tuned to identify the dependency, and accordingly it has to shuffle the instructions on its own in such a way that it is not going to affect the result of the program. And then the next level of parallelism which we are going to focus is task parallelism. Here the task parallelism employs the decomposition of the task into subtasks. So the main task is going to be divided into subtasks, and these subtasks are identified in an independent manner, and they can be executed by the processors concurrently. Okay, so subtask is nothing but collection of instructions. So multiple instructions grouped together to satisfy one subtask. So these subtasks can be distributed across different processes, and these processes can execute the subtask simultaneously. That is what we call as task level parallelism. Then comes data level parallelism. Here, the instruction from single stream will operate concurrently on multiple set of data. And usually, when we want to operate on an array of data or vector data, that can be quoted as a very good example for data level parallelism. It is often limited by non-regular data manipulation patterns and by memory bandwidth. If the memory is not able to supply the data at a faster rate, then I think parallelism may not be achieved. So we have discussed how parallelism can be achieved at the bit level or at the instruction level or at the task level and then at the data level. Then we are going to discuss about the architectural trends. So coming to this architectural trends, how we are going to get the support of the architecture to realize these operations. So when multiple operations are executed in parallel, many cycles are required to execute the program, and of course these cycles are going to be reduced. So, however, the resources are needed to support each of the concurrent activities. So, here by resources, what we mean the number of registers that are going to hold the intermediate data, the number of functional units which are going to be involved in performing these operations. So, resources are allocated, are also needed, and they have to be allocated to the local storage. Only if they are allocated to local storage, then the processors can handle the data individually. The best performance is usually achieved by an intermediate action plan, which can make use of high degree of parallelism and also high degree of locality. So generally, the history of computer architecture can be divided into different categories based on the component which we have used. So namely the vacuum tubes, the transistors, the integrated circuits, and VLSI. So at the architecture level, how we will be able to achieve parallelism, that is going to be discussed now. Now, till 1985, the duration was dominated by the growth of bit-level parallelism only, and then we had the concept of 4-bit processor followed by 8-bit, 16-bit, 32-bit like that. And whenever we want to reduce the number of cycles required to perform the operation, we will just feed the data with data path, doubled data path, and thereon the 64-bit operations were introduced. Okay, and in the mid of 80s and 90s only the instruction level parallelism came into picture. So we have discussed the four level of parallelism, and these parallelisms have evolved in the history at different milestones. And then the risk approach showed simple pipeline technique to improve the overall performance, and the growth of the compiler technology also plays a major role in improving the overall performance in terms of parallel processing and also in pipelining. And of course, in the mid of 80s, the microprocessor based computers were evolved, which contained a different integer processing unit, a floating point unit, a cache controller, and the static RAM for the caching the data, and then for tag storage. So we have separated integer processing unit and floating point unit, and that itself is going to support a kind of parallelism. As the chip capacity increased, all the components were merged into a single chip, and of course the single chip will consist of separate hardware to handle integer arithmetic, floating point operations, memory operation, and pipelining branch operations. Other than pipelining, individual instructions will fetch multiple individual instructions. When the infrastructure is able to support fetching of multiple instructions, then also parallelism can be extended. In general practice, only single instruction will be fetched. After fetching, it will be decoded, then it will be executed, and then we will store the result back. If we are able to fetch multiple instructions at the same time, then I think the performance can still be improved. And this particular concept demands separate hardware support. And of course, we will explore that in the next session. Thank you.